So it's a really pleasure to be here. It's been an exciting 2 days. So I actually sat many times on your side of the table. So actually, I sat sort of way in the back usually because then I had a good view of the room. And actually, I've always enjoyed the presentations a lot, but I always wondered about Microsoft products. I was wondering, what is there in the product vision that we don't know about? And therefore, I thought what I'll do today is I'll start a little bit with the product that I'm working on, which is Microsoft Teams. And then I'll talk a little bit about the challenges that we have in building it and some of the challenges that I see going forward and how we as computer scientists will work in the future. Let me start with a short video.
Over the last few years, we've seen how digital transformation has shaped a new culture of work. From cubicles and silos to collaborative workspaces. From rigid hierarchy to more flexibility, openness, and inclusion. From individual achievement to teamwork and shared success. From limited data to boundless information and insights. As the stakes get higher, we're expected to be more creative, to get more done with less, and to deliver results faster. At the same time, digital technology continues to advance in exciting ways. And a new kind of workplace is emerging. An intelligent workplace, where AI anticipates our needs, simplifies our tasks, and extends our capabilities. And we at Microsoft believe this new technology is not just for a chosen few, but for every person in every organization, empowering each of us to work together, across teams, across countries, and across languages, meeting and exceeding new demands. This is the future of work, an intelligent workplace for everyone.
So let me talk a little bit about this in the context of Office 365, which is sort of the application that I know most. So if you think about digitalization, what it allows us is it allows us just to do more, but also create more. So in Office, we have about 180 million monthly active users. They actually set up about 1 billion meetings every month. They create billions of documents every month. And sort of with this flood of content, we actually have to have ways of organizing it, of sifting through it, then finding out what's important, devoting time to that, then and passing it on to the next person, the collaboration. And so what we've also seen is that not only this digitization is driving massive amounts of data, is that the modern workplace is changing itself. So if you look at how organizations are working, mobile and social tools are much more prevalent than before. So about half of the workers, they now use social tools at work. We've seen over the last 5 years that workers have, or employees have 4 times as many devices per user than before. I mean, there's some users that just live directly on this kind of device. And it's also a little bit of a generational thing. And that means if you look at our workforce, it becomes much more diverse and global. So there are studies that say they claim they have 5 generations together now for the first time in the workplace. That sounds a lot to me. But even if I look at sort of my teams, they're definitely globally diverse in that I work with teams in Vancouver and on the West Coast. But I also work with teams in Prague. I work with teams in Tallinn. I work with teams in Oslo. So I work with teams all across the world, and there are both cultural differences, and then there are also, of course, differences in time zones. And then, of course, team dynamics is also changing. So every worker is now on average on twice as many teams, and about 80% of the time, therefore, is spent collaborating. So what we've done is we've designed this product, Microsoft Teams. Did anybody actually get a chance to sort of play a little bit with it? Who got a chance? OK, a few people at least. So I'll be fast. So Microsoft Teams is basically the new hub in Office 365 that we've designed basically to address these challenges. So what it does is it allows you to connect the dots. So first of all, as you think about meetings, a meeting is not an isolated piece of your workplace. It's something that weaves in the information fabric of your whole digital life. So therefore, what we've made sure is that in Microsoft Teams, we can actually work not in silos across apps, but we actually weave all the Office apps into a single surface. There's actually a great book by Patrick Lencioni called Death by Meeting. Has anybody read this book? Patrick Lencioni is actually one of my favorite authors. He writes these business fables. And so in this book, what he talks about is, he talks about meetings, and there's a whole story around it. And then he comes to the conclusion that meetings are usually not effective, and they're boring. And so we're trying with Teams actually to address at least one of them, namely they're not boring because they actually have all the context now here. So actually once you have the right context, then meetings are actually effective. For boring, what Lencioni says is, well, you have to have drama. And we're working on that a little bit more. Then, of course, we want to be inclusive, right? That people who have lots of different ways of interacting, maybe chat, maybe email, maybe face-to-face, that they can be included. And then, of course, we want to work as a team. And this notion of going to a team and to a people-centric notion of work is actually now making through all of our apps. There's actually quite a different way of thinking how Office 365 works, right? If you think about Office 365, you think about Word, Excel, PowerPoint, right? You think about sort of all these different apps, but you don't think about people at the center of it. And if you think about Teams and actually how we're reorganizing and connecting all of our apps, we're putting people at the center of the work. OK, I'm being very quick on this, but this is Teams. It's basically the hub for teamwork in Office 365. The first capability is simply communicate. So you can have one-on-one chats. You can have open chats in channels that are in Teams. You can very easily have meetings, and you can have all the collateral for meetings together. You can call. You can very easily have a one-on-one chat and escalate in a call. Or, of course, you can set up meetings in which you have calling as well. You can very easily collaborate. So in a chat, you can actually embed Office documents. You can directly open them in the app, and then you can directly collaborate in the Office documents directly in the flow of your work. It's customizable and extendable, so we understand now that people don't only use Microsoft tools. So what you can do with Teams is you can basically take all of the other tools and integrate them directly deeply into the app. So it has about more than 150 extensions. And there's also a whole developer platform in which you can extend the app. And then, of course, given that this is Microsoft, it has all the necessary enterprise controls, but also the security and compliance built in from the get-go. Actually, what we're also doing is we're doing some interesting work with devices. This is actually interesting that we're not just taking out devices and slapping Teams on device after device after device, but we think of these devices as an intelligent edge. I don't know if any of you had problems with setting up a meeting where actually everybody has a cell phone and there are a bunch of devices with cameras in the meeting room. And it's really hard to set up this meeting because they don't all know about each other. So with Teams, what we're thinking about as the intelligent edge, that these devices know about each other and then enable very different kind of meeting experiences where the edge actually is connected together. I wanted to talk about one more aspect of the product, is namely that it's not only for the generic information worker, but as the future of work changes and the nature of work that people are doing is changing, we try to address different subgroups and create tools that directly fit into their workflow. So one of the really big communities out there is Firstline workers. So these are the people that are first engaged with customers. They represent a company's brand. They see the products and services in action. This is basically the airline representative who helps you to rebook your ticket if you have a problem. This is the barista at Starbucks who always seems friendly and always engaging. This is the person at a retail store who makes you comfortable when you go into the retail store, or who basically checks you out at the cash register. So these are the people who you directly interact with, and as a company, they represent your brand. And it's actually often a blind spot during all of these digital transformation efforts that we now have. It's estimated to be a population of about 1.5 billion workers. And the daily activities tend to be a lot of what we talk about here in the summit. Maybe they tend to be microtasks. They tend to be very task-specific, but require the integration of lots of different technologies. And if you look at the Firstline workers' technology needs, they are about digital communication, task management, scheduling, then integration of LOB apps, which is basically the integration of other tools in their workflow, and then also access to documents. So let me play one other video about how we're working with Firstline workers.
We base our work culture very much on the Alcoa values, which is operate with excellence, act with integrity, and the one that I care about the most, which is care for people.
We operate 24 hours a day, 365 days a year.
We have to know what just happened, what was happening yesterday. We have to know what's happening tomorrow. Communication was not as good as it could be. All our announcements were coming through email. If I wasn't at work, I didn't see it.
It was a challenge to make sure everybody got the message. It was like shouting out into the void sometimes.
A lot of the challenge is trying to get the correct amount of people for each shift. With the magnetic board, you have to physically be there to try to get the shift. This board was very inefficient.
The goal was connecting everybody, and Teams was the tool we found for this.
It has helped us a lot and made the workplace a better one.
I just go on my phone, I see what shifts are open, click on the shift, and request it. It's really easy.
Being able to use that on a mobile phone is amazing. It's truly amazing.
And then at the end of every shift, we write our shift messages for the next one. We use emojis and GIFs. It doesn't have to be all seriousness. It can be fun.
Teams has allowed me to respond to the people immediately.
We want everybody to be heard, and we want everybody to be equal. We're giving everybody a voice.
Valka was moving forward with each generation, and our generation all have phones in their pockets, so Teams is the future.
Okay, great. So now that you sort of have a bit of an idea of what the product does, let me go through a couple or two or three features, and then let me dive a little bit down into the technology that actually is there that we use to create the product. So throughout the product, we actually use a lot of machine learning, especially deep learning. So here's one simple example.
Too high for the couch. The coffee stand is too high for the couch.
The set of china hit the floor with a crash. The set of china hit the floor with a crash.
So you clearly see the difference between the two different types of audio. Let me move on. Another thing that we hear all the time from our users is that they work in open environments, and especially now these days with offices working more in open space, background noise is a big issue. So let me give you an example here. And this is with background noise suppression. And actually, I'll come back to that because that's actually an interesting problem. Another thing that we did is we looked at the whiteboard that's designed for remote meetings. You probably have done this when you had a collaborator at a different university. Right? What do? At some point in time, things get excited, and then you go to the whiteboard. And once you work on the whiteboard, the remote collaborator is usually disconnected from what you actually do. So what do? You take out your cell phone, you take a picture of the whiteboard. And as the whiteboard evolves, maybe you send a few more pictures. There's actually a bunch of good apps out there. I mean, even Microsoft has one called Office Lens, which basically takes the picture and then automatically crops, sharpens, and enhances it and straightens it and sends it over. And what we've basically done is we've taken, in collaboration with MSR, we've basically made the same idea so the picture basically automatically beautifies itself. But then we added some simple deep learning-based segmentation to filter out the person that's blocking the whiteboard. And the result is basically what you get on the bottom right, where you basically still see the person in front of the whiteboard and for remote people in real time. And you can see sort of what's in front of the person only is revealed when the person moves away. We're still working on trying to see through persons as they're writing. So let me talk a little bit about the technology that's underlying all of this. So first of all, we're relying very heavily on what we call the global media or the delivery network, which is 100,000 miles of fiber, fast private fiber across the globe that Microsoft is using. We have over 100 edge nodes, which basically places us much closer to our users. We have about 2,700 ISP peering relationships that allow us to look at performance based on traffic, even down to the level of the ISP. What this means is that we're actually, for about more than 6% of the GDP of the world, we are 25 milliseconds away. So let's think about audio-video, right? We've seen a bunch of audio-video examples now here. Let's actually dive into the audio-video stack of Teams and Skype. This was all new for me, actually, so because as you may know, I work on database systems, so this was actually a great learning experience for me. And so if you look at an audio-video stack, right, there's basically the data plane on the top where you capture, encode, and send, and then receive and decode, and I'm being a little bit abstract here. And then at the bottom, you have the control plane where you basically capture, then you do rate controlling, quality controlling, and bandwidth estimation. So the interesting thing is that this is actually quite a complex scenario because it has to work across a wide variety of different types of networks, from 2G all the way up to LAN. And a variety of platforms, of course, Windows, Android, iOS, a wide variety of hardwares. Right? We talked about the intelligent edge. It cannot only work on smartphones and PCs. It has to work on a wide variety of embedded devices as well. And then, of course, taking power conditions into account. Right? If my phone is running low on battery, I want to behave differently than if I'm fully charged. And so if you look at this red part of the stack down here, it's only at least 150,000 lines of code, right, if I'm not too generous. It has about 1,000 hand-tuned parameters, and maybe some of them were tuned with A/B tests. They've evolved over the last 15 years, so there's a lot of expertise, a lot of domain knowledge of networking experts and codec experts and everybody. A lot of PhDs actually built this piece of code. And so the process, what we're doing right now is we're trying to replace this red part with this green part. So basically, we're taking the red boxes and replace it with a magic green box. No, that's not what it really is, right? What we're doing is we can replace the whole control plane basically with a model. And now this model gets all the inputs and makes all the decisions. And maybe what we should be doing is we should actually replace everything with a model, right? Why stop at the control plane? Maybe we should take the whole data plane and replace it with a model. And actually, I see some nodding from the audience here. That sounds very logical, right? And as you know, so this actually now changes quite the game in which we work, right? On the left-hand side, we have a lot of code. On the right-hand side, we have a much simpler architecture. And hopefully, we have no more hand-tuned parameters. On the left-hand side, yet all this learning conceptually that's now encoded in the code was done by developers, and they added new code and rules. On the right-hand side, there are no hard-coded rules anymore. Everything is automatically learned from data. On the left-hand side, we have a lot of experts. They're experts in networking and codecs with a steep ramp-up time. People did their PhDs on this. On the right-hand side, we have sort of much more fungible people. We have people who need basic expertise in machine learning, deep learning, and reinforcement learning. And on the left-hand side, basically, also when we have new networks or new codecs, then we need to write new code and new rules. We need to write exceptions. On the right-hand side, well, maybe we just need to collect a little bit more data and retrain the models. Everything is done, right? That's how every paper would be written, right? Now, and actually, I'll tell you a little bit what's the difference to a paper in a second. But basically, this is now called Software 2.0, as many of you know. Where on the left-hand side, you basically program with code. And on the right-hand side, you program with code, data, and models. While on the left-hand side, you have domain expertise. On the right-hand side, you have ML expertise. You transfer the expertise to code, or you collect data. Code complexity now is transferred into data plus search, which gives us models. The left-hand side gets better with more code, or smarter people. The right-hand side gets better, hopefully, with more data. The left-hand side is potentially hard-coded and brittle, and the right-hand side just adapts with more data and learns the new conditions. And really what I do is very different. On the left-hand side, I write code. On the right-hand side, I probably need to write some code as well, right? I need to write some framework code to make everything working. But really what I do on the right-hand side is I label data. So the interesting thing is that this is not only a way in changing off, moving to machine learning, but it's a change in process. Right? So if you think about it at a high level on the left-hand side, I release, define some tasks, design modules, then I have some release mechanism, write and reuse code, and then I debug, and then I release. On the right-hand side, okay, I define the task as well. Then I collect data and labels, and it's actually a major task. Then I prepare the data and train the model. That's actually another major task. And then I debug, release, and so on. And this is actually a very different process than the process on the left-hand side. Right? This model that I have there, on the left-hand side, the code that I used to write, we're trying actually to prove properties about this code. We're trying to make this code as deterministic as possible, that we can prove correctness of a program. Right? We can write specifications of programs and then directly translate them into code. On the right-hand side, now I have this model in there. Wow, it's like a doctor that I'm treating a patient. Right? I sort of have to help this model to actually understand whether it's performing well, where it's performing well or not. I'm sort of much more of a scientist on the right-hand side than on the left-hand side, an engineer. So I want to tell you two stories where I've actually sort of seen this shift towards data-driven decision-making and models in there directly here that I've directly experienced. One of them was in a startup that I worked in, and the other one is here at Microsoft. So this startup was called Fast Search and Transfer. Actually, it was two of my colleagues formerly at Cornell. They introduced me, and then we worked there. It was basically a search and business intelligence company. And so we had clients such as, in finance, e-commerce, government, and retail. We had clients such as Washington Post, Nordstrom, Marriott, and so on. The main point is what we were selling enterprise search. So it's different from internet search, where enterprise search basically captures everything that is inside of your company. And there are people who have worked a lot on enterprise search. I see Sue here, right? There are lots of experts here. But basically, enterprise search is very different from internet search in two different reasons. Two main reasons. There are a bunch of others. The main reason is that there are very few links. Right? So the link structure, John is here, right, with Hubs and Authority. So the link structure that's being used to actually rank or get strong signals in the web is not there in the enterprise. The second thing is there are very few clicks. Because I might have a company that has 50,000 employees, but still has 1 billion documents. Right? So the amount of engagement that you have, the click-through rate, because it's not on a single global corpus, is also very different. And of course, at that point in time, our semantic understanding of documents was much lower because we didn't have all the cool DNN embeddings and so on that everybody uses right now. Now, if you look at enterprise search, it's really powered by the power of data. So what we can do is actually, this is when I joined Microsoft for the second time in 2013. We built what's called Delve and the Office Graph. And what the Office Graph basically is, it basically makes all the signals that belong to a company available through a programmatic API. So we basically have collected all the signals across Office 365 and made them available as a data asset. So look at the Office Graph up there. It's called now the Microsoft Graph. So we have a user, we have chats, calendar, messages, files, groups, et cetera, et cetera. So especially what this means is suddenly now through people in their interactions with content, we actually now have signals or indirect signals on documents. And so what we can now do is we can now actually change, first of all, the way we discover content by looking at an entity-centric way of discovering. For example, we can use people as a hero entity. And this is an application that we built called Delve, where you basically go to a person, and then there's a relevant feed of relevant content around that person based on all of these signals. In addition, we can now use all of these signals as well to make enterprise search much better. So this is story number one. Story number two is actually going back to Skype and Teams. Let me talk actually about an application directly here, which is just capture quality enhancement. So same picture with the same colors. Right on top, we have now our sort of a little bit simplified voice capture quality pipeline. Right? So you start out with analog gain control, then you do some echo cancellation, then you do noise suppression. Then you have a voice activity detector, then you have key tap suppression, then you have digital gain control, and afterwards you have some howling, some echo suppression. So what we're doing is, again, we're taking a bunch of these red boxes and replacing with a green box. And by the way, there's an interesting question, right? There's componentization that comes out of software 1.0. And should we keep the same componentization in software 2.0, or should we just collapse everything into a single model? So what we can do now is we can basically train this green model. Well, so how do we do this? It's very simple. Well, we just take noisy data. It's just clean plus noise, and we can generate a lot of data like that. And then we minimize noise minus clean, right? Or minimize some other objective function. And there are lots of other approaches, right? We can do adversarial, we can learn the noise through a GAN, or we can do source separation approaches. So this is just an example of the kind of work that we're doing. And basically, we think we can actually get significantly better noise reduction with this.
Their curiosity went happily out of bounds. Their curiosity went happily out of bounds. Their curiosity went happily out of bounds.
So this is always, noisy, then with the existing tech, and then with deep learning. So this is battle noise. Let me do one other one, and there's lots of different types.
Eternity is no time for recriminations. Eternity is no time for recriminations. Eternity is no time for recriminations.
So you basically heard there was basically no difference between the first and the second. And the reason is that there's basically a Wiener filter in the current algorithm that basically sort of takes out Gaussian noise. And Gaussian noise and people with chips crunching is not Gaussian noise. Okay, so actually the interesting thing is what we did is we didn't only learn the noise suppressor. Actually, we sort of looked one step ahead. Namely, what we did is we trained actually a model that looked at the output of an audio call, and we trained a model that would actually directly assess the quality of the call at any point in time. So basically think of this sometimes at the end of a Skype call, you've probably seen this, one of these call quality feedback tools pops up. You know, how was the call? So think what we basically have done is we've basically created this no reference audit quality predictor, which basically listens into a call on your client side, completely private to you, but it can constantly give now a thumbs up, thumbs down. How is the call? And that can now be used to actually then, even this model can now be used to train the noise suppressor, which then goes in and suppresses the noise. And actually, sort of this replacement of code and with models is now happening in all areas of computer science, right? The whole summit was full of this, right? One of the areas that I know a little bit about is database systems. And and database systems actually happening all over the place, right? There's the query optimizer, of course, and selectivity estimation, so people have looked into. But there'll be other areas like query optimization and query rewrite together, right? Selectivity estimation already mentioned. There will be, if you do query optimization already, why not optimize the physical layout right away as well, right? Why not look at resource management overall in the database system in general, right? So again, you can think of this like the control plane of the database system can be replaced with a model as well, right? So basically, the importance of like traditional approaches will sort of shrink, and the importance of other approaches will grow over time. Okay, let's go back to background noise suppression. So what did we actually do? Well, we did all of these steps, right? We created synthetic data, did some ground truthing, created some reference data, created some gym, trained in the gym, right? And then A/B test and repeat. So actually, these steps are common to most machine learning projects. And what's interesting is that train the models there in step 7, right? You define the data, identify data sources, collect data, define some tests for data calibration, define data unit tests, build a gym. Then you train the model. You debug and improve the model, deploy the model, monitor, collect more data, and repeat. And every time we interview candidates, they're most excited about 7, right? This is where all the excitement is. When you look at papers, the improvements are always here. This is so super important and really exciting. However, if you look at where actually the time is spent, right? The time is not spent on step 7. Right? The time is spent on all the other steps. So actually, less than 10%, on the project that I have done, less than 10% of the time is spent on 7. Actually, we're getting very good on 7. Right? We're creating AutoML, right? We have architecture search. We have lots of hyperparameter search algorithms. So while training the model is fun, right? We're spending a huge amount of time on all the other steps around it, right? And again, sort of if you talk with candidates, right? They're again excited about training the model, right? They want to understand, well, should you use ReLO? What is the number of convolution layers, right? The initialization should be this. The learning rate should be this, right? What should the learning rate decay be over time, right? Should I use an L1 or L2 norm, right? All the steps that we're, as researchers, are excited about because we can technically quantify them. Right? Here's another thing. I love step 7 because I can basically automate it through differentiation. Right? So basically, this step here, there's a procedure behind it, and then it gets completely automated. What I would love to do actually is I would love to take all of these steps, differentiate across all of these steps together. Unfortunately, I can't do this yet, right? Because we haven't made enough progress to actually take all of these steps together. Okay. So going back to the change in process. So actually, when I showed you the slide, I sort of lied a little bit, right? And I was sort of not telling you all the details of 1.2 versus 2.0. So actually, let's look at 1.0 in a little bit more detail. So the way to think about software, actually, the software development process in 1.0, there are actually 2 different cycles. There's the inner cycle, which is basically, you edit and write some code, you then build it and debug it. Think of this as just me working, on my PC or on my laptop, and basically working for me, myself. Then there's the whole outer cycle. The outer cycle is basically now where I work together as a team. And this outer cycle is super important. And there's a ton of tooling around this, right? So let's start out basically by, now I check in, now the code gets reviewed, there's a review code. Then there's testing. There's a continuous integration pipeline. There's a release management process. There's monitoring. There's issue management. There's documentation. There's analytics, which actually shows me whether A/B tests were correct or had any impact. So actually the pipeline in Software 1.0, we call it computer science, but this is really software engineering. So this is really an engineering process. So what we've really done is we have basically taken all the steps that you've made and basically made it an engineering discipline. And that's why companies such as Microsoft, we can scale software products and projects up to like 100+ developers. Otherwise, we couldn't effectively collaborate. So what's actually now changing? Right? So if I look at 1.0, well, I have a traditional program tree, right? This is sort of a stack trace here. Now in 2.0, basically, I replace some of these boxes, maybe with a learned function, maybe with a deep net, maybe with a deep net and some human code, maybe some guardrails, right? And I can do that right for a regular program. I can, of course, do the same thing for a data stream program where I directly go from data to some action. And the difference is basically that on the left-hand side in 1.0, basically, we have all this tooling around it to have made this basically a production pipeline into an engineering discipline. And so I would argue that on the right-hand side, we are starting to get some tooling. We're starting to learn more, but we're still very much in our infancy. So let me talk for a few minutes about this. High-level abstractions. Okay, so this is like computer science undergrad knowledge, right? We have learned a lot about how to hide complexity from the developer. I don't know whether anybody went to the talk, what we did about what we're doing in Visual Studio, right? I mean, Visual Studio is an amazing tool. For example, the interactive feedback is actually amazing. The syntax highlighting, of course, the code auto-completion, right, which is actually really interesting as well. But we have all the way from like high-level memory-managed languages, declarative languages. I actually love SQL. Right? It's actually the most successful parallel programming language, I believe. Then we have ways to hide asynchrony, right? We have future promises and other asynchronous programming support. We have intelligent code refactoring, where actually the process of refactoring is hidden from the programmer, and so on. This is probably an incomplete list, but on the Software 2.0 side, actually the list, it looks like research projects there that we have, right? We have machine teaching, right? And we talked about machine teaching here at the summit as well. But I think it still needs quite a way to go before it's an engineering discipline, right? We have weak supervision, and Chris talked about Snorkel and how it's being started to be used. I would say it's also not yet really at an engineering discipline level. Right? We have AutoML and model selection, hyperparameter tuning. Maybe that hides a lot of the complexity of building the model, actually. Maybe we have separate data engineers, data scientists, ML engineers, and maybe ML applied data scientists. So we're sort of starting to branch out into different sub-disciplines, but I don't think we have the final answer yet either. We have some pre-trained models, right? BERT and GPT-2 and so on, and it's very easy to import them into Python and other tools. So I think we're getting there in terms of we're making good progress, but we're by far not as far as on the left-hand side. Another interesting question, of course, is debuggability and debugging in general. So debugging is of course about diagnosing and fixing errors and other undesired behavior. Right? On the left-hand side, we actually have really good support. Debuggers, breakpoints, stack traces. Right? We have code analysis tools. We have log analysis tools. We have anomaly detection. We have tools where you can collaborate with somebody else and work on it. On the right-hand side, or on the bottom here, we're getting there, right? I mean, I think this comic actually explains it well, right? This your machine learning system? Yep. You put the data into this big pile of linear algebra and then collect the answers on the other side. Well, what if the answers are wrong? You just stir the pile until they start looking right. Right? So basically, while, again, in Software 1.0, this is much more of an engineering discipline. It's much more of a science and maybe even a little bit of an art right now to train models that have the right performance and get the right pipeline right. There's one other interesting question. And I think that's actually an open research question. Namely, this is the whole notion of debugging and explaining. For code, we know how to do this, right? So Sue and I can sit here together. We can look at this program and understand where the bug is. Does anybody see where the bug is? But see what you're doing. We're all staring at the code, right? We look at this code, right? So actually the problem is that curmin may not be initialized, right? And therefore it may take on some crazy value, and that value is then returned. But what if I cannot look at the data that I'm using to train my model? Right, so I joined Microsoft maybe 6 years ago, and one of the things I was most impressed by was how seriously Microsoft takes data privacy. So this is not about security. It's not about people, attacking our cloud. That is, of course, P0. That's absolutely important. But I have never seen a single piece of customer data. Even within the enterprise, there are very strong barriers that I cannot look at somebody else's data unless this data is open and shared, right? And we have an open and shared workplace. But we take extreme care that no engineer can ever log into any machines, cannot look at any of the data unless the customer explicitly gives us permission, for example, if this is in spam email and the customer marks it like this. But they're like layers and layers of protection and escalation that prevent anybody from looking at any data. So we can stare at this piece of code together and look at it and collaboratively find the bug. How do you do this with data? What are the right tools if I'm not allowed to look at the data? In addition, for what population can I build a model? This is another interesting question. So clearly, I cannot build a model for Microsoft and then use it for another company because it may leak some information about Microsoft to another company. But even within Microsoft, if I look at documents, documents have different ACLs. So I might be able to have access to a document, but Sue might not, and vice versa. So what this means is that even if I were to build sort of a model across all the documents, the set of documents that I have access to is constantly changing. So how do you do machine learning in this kind of an environment? The last thing is data attacks. So I think this is another very interesting question, namely, if we have this continuous integration pipeline where basically we collect more data, we update the model gets automatically built, and it gets automatically deployed if it passes sort of a certain set of tests, and so on, and you can argue, well, the model gets better and better and better, and we maybe build some shift into the model that it sort of forgets old data and only learns from the most recent data. Well, this is super worrisome, right? Somebody could could go ahead and attack the model with biased data and then make the model perform much worse than it did, or discriminate a certain type of population. So this is debugging and explaining. Testing, again, in testing, I think we have a bunch of really good engineering tools on the Software 1.0 world. In Software 2.0 world, we're getting there, right? Maybe the most interesting thing is data and model provenance, maybe a data review process, especially if you look at bias and fairness of data. It will be an iterative process. Continuous improvement, this is sort of one of the big issues as well that I talked about, where we had this really big cycle there. Right? We have a lot of tools in Software 1.0. In Software 2.0, well, we're again starting to learn, right? We have maybe data quality engineers. Maybe we have ways to detect and respond to changing input conditions and environmental conditions, right? Maybe we use online and reinforcement learning. Maybe we need something like a GitHub for data, like a GVC. Right? We have AutoML that trades off accuracy for speed or memory footprint. With quantization, we have specialized chips. So there's a bunch of work that's actually happening here in this space as well. But overall, I think the message that I want to land is that as we have software as an engineering discipline in 1.0, I think we need much more work to really make the whole software development cycle, the whole software life cycle, to make that an engineering discipline. So with that, I want to call for action, and I'm getting to the end of my talk. I know that I'm between you and a good reception at the end of the day. So we want to collaborate. I think there are lots of really great open problems here that I think all of you have a ton of expertise. We would love to collaborate with you. There are many ways of getting resources. We announced the Microsoft Productivity Research call for proposals. There's the Microsoft Research Open Data. Actually, Microsoft Azure released a VM data set in 2017 for the SSP paper. That's the third most cited SSP paper from SSP 2017. They just released a new version for the Faculty Summit. It's basically 162 million hours of VMs and resource usage, about 1.9 billion recordings that we can all use for research analysis. And then, of course, please send us your students for internships. So with that, I hope that we can do more like the following together.
Being both technical and creative.
So I just wanted to check in with you guys and talk about
democracies respond to those scandals. My apologies.
Thank you very much.